This is the third video, and in this video we are going to talk about problem number 11 of our first exam. In this problem, we are given INs to be the n by n identity matrix, 0 be the n by n zero matrix. The hypothesis is that we have a square matrix A of size n by n with A squared equal to 0. We want to show that under this hypothesis, the matrix In plus A is invertible, and not only that In plus A is invertible, the inverse is In minus A. This is actually a very easy proof utilizing nothing but the definition of an inverse. But before I show you the solutions, let us look at some of the common mistakes the arguments make for these particular problems that we're not going to fly. One of the mistakes is that saying that the matrix multiplication A squared equal to 0 will implies that the matrix A itself has to be 0. And this is not true in general. For example, if we have a 2 by 2 matrix A, which is with entry 0, 1, 0, 0, we can show that matrix multiplications A with itself, which is our A squared, is going to be the 0 matrix, 0, 0, 0, 0. But clearly you can see that A itself need not be a 0 matrix. So any arguments involving something that saying that A squared equal to 0 implies that A equal to 0 is not going to work. Another attempt, which is a common mistake made during the exam, is to say that the determinant of In plus A is equals to the determinant of In plus determinant of A. Now this is not going to work in general. We do not have a formula that looks like this. What we have is something that is like determinant of A times B equals to the determinant of A times determinant of B. We do not have this. This is not true in general. What we have is saying that if you have two matrices A, B, they are both square matrices, then the determinant of the product of that two matrices is equals to the products of the determinant of that two matrices. Another failed attempt is to try to compute the inverse of In plus A directly. So they put In plus A in here and then In here and try to row reduce everything so that you have In here, and by theorems, whatever you have here is going to be the inverse of In plus A. Now these methods will not work because we do not have information on the entries of the matrix A. So we do not know what A11 is, we do not know what A12 is, so you cannot do row reduction without knowing all that information. So these are the attempts that a lot of you try to make during the exam for this particular problem, but unfortunately that's not going to work. So the way to do this is very simple. Let us recall the definitions of an inverse matrix. So if you have a square matrix P of size n by n, and we say that the matrix P is invertible, if you can find, okay, if and only if you can find another square matrix of the same size, such that the product P times Q and the matrix product Q times P, they are the same, and not only they are the same, they are both equals to the identity matrix. If you have these relationships, then we say that Q is the inverse of P, and therefore P is invertible. So what you need to do is just simply multiplying this thing out, because you already been told that In minus A is going to be the inverse of In plus A, right? So you want to show that. So you try to multiply these two matrices and then use the matrix distributive law. And you can see that once you distribute the whole thing out, you have In squared minus INA plus AIN minus A squared. Identity matrix multiply any matrix will be that particular matrix. So in this case, we have minus A. Here we have plus A, so they cancel out. And then you have In minus A squared. And the hypothesis, this is where we use the hypothesis. The hypothesis says that A squared is 0. We are only looking at those matrices with square, which itself gives 0. So for those matrices, In minus A squared is going to be equals to In. So you can redo this computation again with In minus A with In plus A. Then you can see that it is still In. So by the definition of the matrix, the invertibility of a matrix, we know immediately that In plus A is invertible and In minus A is the inverse. You can also only just show one part of it and use the lemma that we know that the left, so this is the right inverse of this matrix. For square matrices, if you have right inverse, you will have left inverse, and the right inverse and the left inverse are the same. So the solution for this is actually just very straightforward computations that looks like this. One final thing I want to comment is that a lot of students who try to show the products equals to IN has a presentations which I don't think is very nice. For example, this is what I call bad presentations. So this is what you are supposed to show, but instead of showing it, through computations, you immediately say is that you have in plus a and in minus a is equals to in. And then you started to distribute everything out. And at the end of the computation, you have in equals to in. This is not a very nice presentation. Try to imagine that you're going out with a friend for a movie, and then right before the movie starts, you tell your friends exactly how the movie is going to end. Just like here, you tell your friend exactly how the movie is going to end, and then at the end of the movie, kind of like here, you reiterate the facts that this is exactly the same ending as you told your friend in the very beginning. I'm pretty sure your friend is not going to be happy with it. So this is actually, presentation-wise, this is actually pretty problematic. I know that you've been doing this a lot in high school proof. For example, proof the identity is equal to this or that, and then you do this computation and show that 0 equal to 0. Try to not to do it like that, because logically it just doesn't make sense. So instead of showing, instead of saying this is in, you should just drop this and then do all the computation that is necessary, and then show that at the end you do have ins. Do not make the assumption that it is ins to begin with. Then everything will be better. This is the end of this video. I'm going to see you in the next and final video, which we were going to talk about the last problems of our exam.